Okay, good day. My name is Engineer Tolentino, and I'm going to discuss now the seventh lesson of the course Differential Equations. It is integrating factors. Okay. A first order differential equation of the form mxy dx plus nxy dy equals 0 is said to be generally a non-exact equation if the partial derivative of m with respect to y is not equal to the partial derivative of n with respect to x. Now, a non-exact DE may possibly be converted to an exact DE by multiplying it by a suitable integrating factor. Okay. Now, if I say that mu xy here is an integrating factor, then okay, multiplying this differential equation mxy dx plus nxy dy equals 0 by that integrating factor will make this differential equation exact. Look, I multiply mu xy, okay, to both sides of the equation here. It becomes mu xy m dx plus mu xy m dy 0, and this is now exact. Our objective is to determine, okay, what is this integrating factor. Now, let us consider a non-exact ODE mxy dx plus nxy dy equals 0. Alright, generally, the partial derivative of m with respect to y is not the same as the partial derivative of n with respect to x. Now, if mu is a factor that will make the given ODE exact, mu is called an integrating factor. Now we are going to multiply both sides of this differential equation by and it becomes mu m dx plus mu n dy 0. Then this ODE is exact. Now, since this is exact, okay, this should be the condition that the partial derivative of mu m with respect to y, okay, equals the partial derivative of mu n with respect to x. Now, simplifying this, okay, this is a product. This is mu times the partial derivative of m with respect to y plus m times the partial derivative of u with respect to y must be equal to mu times the partial derivative of n with respect to x plus n times the partial derivative of u with respect to x. Now let us transfer, this part here in this side. So you get what? You get mu partial derivative of m with respect to y minus mu partial derivative of n with respect to x is equal to negative m partial derivative of u with respect to y plus n partial derivative of u with respect to x. Now, let's factor mu. It becomes partial derivative of m with respect to y minus partial derivative of n with respect to x equals n partial derivative of u with respect to x minus n partial derivative of u with respect to y. Now, let mu is a pure function of x. Okay, if mu is a pure function of x, then the partial derivative of u with respect to x becomes a total derivative already, du dx, and the partial derivative of u with respect to y is equal to 0. Then we will have to plug it here in this equation. Okay, we have mu partial derivative of m with respect to y minus partial derivative of n with respect to x is equal to n du dx. Now, okay, this is a variable separable already, dividing by mu and then partial of m minus y minus partial of n with respect to x. This becomes d mu over mu is partial derivative of m with respect to y minus partial derivative of n with respect to x divided by n. Now we can integrate, okay, If we let the partial derivative of m with respect to y minus the partial derivative of n with respect to x over n be a pure function of x. Now this, look, this now is what? This now should be what? Should be a pure what? A pure function of x. Okay, therefore we can integrate now. Then d mu over mu becomes f of x. Integrating both sides, okay, you have integral of d mu over mu is integral of f of x dx. We have ln of mu equals integral of f of x dx. And finally, we have an integrating factor, mu is equal to e to the integral of what? Integral of f of x dx. So this is, okay, this is the rule now. Okay, look, this can only be true provided that what? That this portion here, my minus nx over n, is a pure function of x. Now let us, okay, I'm going to use this again and consider now mu as a pure function of y. Okay, so I had this. Now if what? If mu is a pure function of y, then we have partial derivative of u with respect to y is d mu dy, and partial derivative of u with respect to x is equal to 0. So, okay, I'm going to use this again. Mu partial of m with respect to y minus partial n with respect to x is equal to, I substitute n times, okay, times 0 minus m times du dy. I use this equation. And this becomes again mu my minus nx is the same as negative m d mu dy. Separating the variables, you get d mu over mu is partial derivative of m with respect to y minus partial derivative of n with respect to x divided by negative m. Now, if we let what? My minus nx now over n be equals negative g of y, which is now a pure function of y, then this will give you d mu over mu equals negative g of y dy. And integrating both sides, integral of d mu over mu equals integral of negative g of y dy gives you mu is equal to e to the integral of negative g. Of course, this is ln of what? Of course, this is ln of, this portion is ln of what? Ln of mu is equal to what? Negative g of y. So you can what? And then you can solve for mu there. So let's have a summary of what we did. Okay. If 1 over n my minus nx equals f of x, then an integrating factor is e to the integral of f of x dx. If 1 over n my minus nx equals g of y, then an integrating factor is e to the integral of negative g of y dy. Now, let's have an example. Let's solve this equation. Y minus xy dx plus x dy is 0. Again, our m is y minus xy and our n is x. Always remember that m is associated with dx and n is associated with dy. So get the partial derivative of m with respect to y. Okay, treating what? X as a constant, it gives you 1 minus x. And partial derivative of n with respect to x is 1. Notice that these two are not the same. Okay, so let us use the rule. 1 over n my minus nx is equal to 1 over x, and then what? Partial derivative of m with respect to y is 1 minus x minus 1. This is negative 1, which could be written as a pure function of x. So it's possible for us to get the integrating factor. Let's use the other formula. Is 1 over my minus nx. This is the same as 1 over 1 minus x times 1 minus x minus 1. That's the same as negative 1 over 1 minus x. This is not a function of y, so have we cannot compute any integrating factor here. So the only thing that we will use is this one. So our integrating factor now, based on the formula that we have derived, is what? Is e to the integral of negative 1 dx. This is the same as e to the negative x. So this is an integrating factor. We are going to multiply e to the negative x to the left and the right side here. It becomes e to the negative xy minus yx dx plus e to the minus x times x dy is 0. Now again, let us get m and n. Our m is e to the minus xy minus e to the minus xxy, and our n is x e to the minus x. Let us test for exactness. Okay, get the partial derivative of m with respect to y. Okay, treating x as a constant, this gives you e to the negative x minus x e to the negative x. And then the partial derivative of n with respect to x, this is a product now, is equal to x times the derivative of e to the negative x, that is negative e to the negative x plus e to the negative x. So therefore this is exact, and we can use the concept of solving exact differential equation. The simplest method to do this is integrate this portion here, okay, from 0 to y, and plug what? Plug the value of y, okay, plug the value of 0 to the values here. So this is 0 and 0, so basically this will become 0. So integrate this from 0 to y, x e to the minus x dy, and that is e to the minus x here. You plug it here. 0 minus what? 0 here, you plug it here, minus e to the minus x times 0. So basically, this portion here, this portion there becomes what? 0. So this cancels out only, and you know that this is x e to the minus x is a constant here, so you have just to insert y. Okay, you have to just insert y there, and this is our what? This is our general solution. Okay, let's have sample 2. Okay, let's have 2xy squared minus 2y dx plus 3x squared y minus 4x dy is 0. Again, our m is 2xy squared minus 2y, and our n is 3x squared y minus 4x. Okay, get the partial derivative of m with respect to y, treating x as a constant, so it becomes 4xy minus 2. Get the partial derivative of n with respect to x here. Okay, treating y as a constant, so you have 6xy minus 4. This is not exact, so we're going to use this formula. Okay, let's check if this becomes a function of x only. 1 over n my minus nx, that's the same as 1 over 3x squared, sorry, should have been this denominator should have been, okay, this denominator should have been what? 3x x squared y minus what? Minus 4x. Okay, this should have been what? This should have been 3x squared y minus 4x. Okay, notice that if we substitute the value, You substitute the value of my minus nx there. Now this, okay, this will not what? This will not simplify to a function of x. So therefore, there is no integrating factor for this one. So this is not a function of x. This is actually what a function of x and y. So we cannot use the formula that we have derived. Okay, let us check now 1 over my minus nx. That is 1 over 2xy squared minus 2y times what? That's here 4xy minus 2 minus 6xy minus 4. That gives you 1 over 2xy squared minus 2y, 4xy minus 6xy, that is negative 2xy, and then negative 2 minus 4 is plus 2. Okay, let's see if we can simplify this. Okay, this is factor 2y there, that is 1 over xy minus 1, and factor negative 2, that is xy minus 1. Notice that xy minus 1 will cancel out as well as the 2 there. So you have only negative 1 over y, which is what? Which is a function of y, which is a pure function of y. Therefore, we can have an integrating factor. Okay, or I use in the formula g of y. So this should have been g of y in our formula, negative g of y. So our integrating factor now is integral of e to the negative of another negative 1 over y. Okay, this is the e to the integral of the negative of the integrating factor, which is negative 1 over y. This is e to the ln of y, which is y. So what we do is we have to multiply both sides of this by y. So what happens is, this is the original equation, 2xy squared minus 2y times, okay, I multiply this by y already, y dx plus 3x squared y minus 4x times y dy is 0. Simplifying, you have 2xy cubed minus 2y squared dx plus 3x squared y squared minus 4xy dy is 0. Then your m is 2xy cubed minus 2y squared, and your n is 3x squared, okay, this is 3x squared y squared, okay, minus 4xy. Let's check if this is exact. What is the partial derivative of m with respect to y? Okay, treating x as a constant, it gives you what? 6xy squared minus 4y. The partial derivative of n with respect to x, treating y now as a constant, is equal to 6xy squared minus, okay, this should have been what? This should have been 4y, because y is a constant. This should have been 4y. So therefore, it's already what? It's already exact, and we can use this method. Okay, integrate this from what? From 0 to x. Okay, that is 2xy cubed minus 2y squared dx, and plug the value of 0 to the value of x in the right side. So this basically this term becomes what? 0. All you have to do is to integrate that with respect to x, treating what? Y as a constant. So you have what? X squared y cubed minus 2xy squared is 0. So this will be our what? This will be our general solution. Alright, this is the end of the discussion. Thank you.